Hi everybody, welcome back. In this video, I will introduce acids and bases. I will go over the Arrhenius definition of an acid and a base, as well as the Bronsted-Lowry definition. So let's get started. What are some properties of acids? Well, acids typically have a sour taste. They have the ability to dissolve metals. They also turn litmus paper red. And they can neutralize bases. In this table, there are a few examples of acids you come across. Hydrochloric acid is a primary component of stomach acid. Sulfuric acid's used in automobile batteries. We'll talk about that in a future video on electrochemistry. Nitric acid's used in fertilizer. Acetic acid is the key component of vinegar. Citric acid's in your foods and your beverages. Carbonic acid is used in carbonated beverages, and hydrochloric acid is great for glass frosting and etching, and phosphoric acid is a biological buffering system. And so those are just a few examples you come across in your everyday life. Some properties of bases: they have a bitter taste. They can have a slippery feel. So if you got some sodium hydroxide, some concentrated solution on your fingers, then it will feel slippery, and that's not good. They turn litmus paper blue. And it neutralizes acids. So some examples are sodium hydroxide, that's used in soap and plastic manufacturing. Potassium hydroxide is used also in soap production and batteries. Sodium bicarbonate, some of you may have cooked with this. This is baking soda. Sodium carbonate is different. It can be a good cleanser, water softener. And ammonia, which is used for detergent, fertilizer, and synthetic fiber production. Okay, so we'll start off with the Arrhenius definition. An Arrhenius acid is defined as producing protons in an aqueous solution. So it produces protons. And what we mean by protons, I want you to think of H plus ions. A hydrogen atom without its electron is essentially a proton, so that's why we call them protons. They don't have that electron anymore. And we're working with aqueous solutions when we're discussing acids and bases in this class. The base produces hydroxide ions in an aqueous solution. Now, I just want to point out that this definition is pretty limited. We're going to learn other definitions. So, for example, the Bronsted-Lowry definition, it kind of broadens the scope of what an acid and a base can be. And then finally, at the end of this series of videos, I'll teach you briefly about Lewis acids and bases, which is the most general definition and encompasses more acids and bases than, proton donors and proton acceptors or hydroxide ion producers. Those definitions are very limiting. There's more acids and bases out there. However, you would explore Lewis acids and bases in an organic chemistry class and beyond that. Okay. All right, so I'm a big believer in trying to visualize what is going on, right? It's one thing to just talk about these definitions, but it's another to visualize what is going on in your beaker. And so this is the phrase I always use with my students to help them begin visualizing the molecules, the ions, the particles that are in their solution. Because once you can visualize and you can draw it out, the better you are at recalling that information or being able to derive it on the spot. If you always ask yourself, what's in my beaker? And the abbreviation I will be using is WIM. So you'll see that throughout my lectures. So for example, if I were to put hydrochloric acid in my solution, and as the name suggests, it is an acid. If I were to put that in my beaker that has water in it, I would see protons in solutions as well as the chloride anion. Right? If I were to put sodium hydroxide in my solution, which acts as a base, I would see the sodium cation, but as well as the hydroxide ion. And so that's the reason why sodium hydroxide will be identified as an Arrhenius base, because it's producing hydroxide ions in my aqueous solution. Hydrochloric acid is an Arrhenius acid, because it's producing hydrogen ions or protons in an aqueous solution. All right. Now, they actually don't exist as just hydrogen ions. They exist as hydronium ions. So hydrogen ions are highly reactive. Once they find a water molecule, they will produce the hydronium ion, which is a polyatomic ion you would have learned already, but now you understand in what context it is formed and where you will see it. The hydronium ion, it has a +1 formal charge. Why does it have a +1 formal charge? Well, let's look at its Lewis structure. So I'm going to check out that oxygen atom. Oxygen typically in a free atom has 6 valence electrons. Looks like we have 6 bonding electrons attached to those 3 single bonds. We divide by 2, minus the 2 individual electrons as the lone pair. And so that's where you get the +1 formal charge. So when you learned the polyatomic ions in your first semester general chemistry class, you would have learned all these charges, and now you can derive those charges based on your knowledge of drawing the Lewis structures as well as calculating the formal charge. So in reality, we're never going to write hydrogen ions in chemical equations or whatever, like in our beaker. We will always draw out the hydronium ion, because that's truly what's happening here. Now, something I want to tie in additionally to what you've learned before. We've learned about intermolecular forces. We've also discussed in previous videos why solutes will want to dissolve in solvents, right? So a lot of that has to do with intermolecular forces. Also, in addition, there is that drive towards entropy. And so second law of thermodynamics, the entropy of the universe is always increasing, and so always be reviewing over that previous material and tying it back into what we're learning now. It all plays a role here. But what is the dominant intermolecular force that's taking place for these two solutions that I have in my beakers? Fantastic. We're looking at ion dipole forces here, right? Because we're creating these ions in solution. And so even though we're drawing the ions by themselves, understand that water molecules are surrounding these ions, right? They're mixing, they're hydrating, they're forming a hydration shell essentially to encourage the mixing to happen. All right. Now I want to go over the difference between strong acids and bases and weak acids and bases. So a strong acid completely dissociates, or also known as ionizes, in solution. And the way we would represent that generically, so we always represent acids as HA. So that is the hydrogen here will be the proton that's donated. So that's why usually we represent an acid as HA. This particular acid will lose that proton. Remember, we're working in water. So that's the other reactant here. The acid donates a proton. It's producing protons in solution in the form of hydronium ions. So it's giving a proton to water. So now water turns into H. Now it doesn't have two hydrogens, it will have three. And H3O has what formal charge? +1. Excellent. And because the acid lost a proton, it's left with A, but it lost a positive charge, so A actually has a what charge? A negative charge. Good. You can always keep track of these charges. You want to make sure that the charge on the left side of the arrow will be the same as the charge on the right side of the arrow. So over here, it is neutral, 0. And when you add +1, -1, you also get 0. So just be mindful of your charges as you learn how to predict these products and your reactions. Be mindful of that. Like, always practice it. Ask yourself, does this have a charge or is it neutral? You know, if it has a charge, why does it have a charge? Something else I wanted to point out here is the arrow. The arrow is going to be a big clue if you have a strong acid or a weak acid. This arrow going completely forward indicates that we have complete ionization taking place. Whereas with a weak acid, it only partially dissociates. And the way we represent a weak acid chemical equation is it looks very similar. We use the same formula for a weak acid, HA, and then plus water. But because there's only partial ionization or dissociation here, we use those equilibrium arrows that we've learned in the previous chapter. The acid, remember, donates a proton. So, producing proton ions in solution, and doing so it's donating a proton to water, and it goes from H2O to H3O. There's that extra proton. And that acid lost that proton, so it's left with a negative charge, and that is A-. Like I said, the only difference between a strong acid and weak acid is the extent to which the reaction proceeds forward. In this one, we are in equilibrium. can only have partial ionization. Strong base completely dissociates in solution, in an aqueous solution. So I'm going to give you an actual example of what this looks like. There's a lot of different bases out there. The only types of bases that we'll be working with mainly are hydroxides. Those are the group 1A and group 2A. Hydroxides are the strong bases. And then we will work with some weak bases, mainly nitrogen-containing weak bases like ammonia and its derivatives. So in this case here, I'm going to show you an example. Sodium hydroxide, which is a very common strong base that we come across. When we mix this with water, the way we represent that is we break it up into its ions. And so we understand that the sodium cation is not by itself, but remember there's ion dipole interactions taking place where water surrounds it, forming a hydration shell. That's where the AQ comes in, understanding that that's what's occurring. And we have the hydroxide ions. Remember, an Arrhenius base donates hydroxide ions in solution. So there you go. And then plus water just to balance the reaction. So when we're representing these strong base reactions, typically we don't have to show the water. It just kind of, it's there, right? It's always there. But we don't have to show it in the final equation because it cancels out. So really we would show just sodium hydroxide aqueous breaking up into the sodium cation and the hydroxide anion. Once again, the charges are the same on both sides, so that looks good there. The reason why you have to show the water for the acids, remember, is that we want to indicate we had the hydronium ion present and not just protons by themselves. All right. Also make note that the arrows, just single arrows going forward, which indicates that complete ionization. And then a weak base, like a weak acid, partially ionizes or dissociates. So that word's used interchangeably. And so the classic example of a weak base is ammonia plus water. Use that double-headed arrow to indicate partial dissociation. We're going to see that water here is going to be the acid to donate the proton to the ammonia. And doing so, if water loses a proton, it's only left with OH. And what is the formal charge of OH? Minus, right? That's the hydroxide. With enough practice and talking yourself through this, I encourage you to teach this to a friend or a family member, just so it really makes sense to you that you're not memorizing this, but you're fundamentally understanding what's happening here. That's my big mantra, is always kind of practice, teach. If you can teach it, then you know for sure that you understand it, and you can identify any areas that you feel weak in. So for example, this is your base. Therefore, water is acting as an acid. Water is going to donate that proton. We get NH4. NH4 is that ammonium cation, and you can draw the Lewis structure and calculate the formal charge for nitrogen, which would end up being +1. If water lost a proton, it's only left with OH, but OH is not neutral. It also has a formal charge of -1. So you could draw the Lewis structure of hydroxide and calculate the formal charge for oxygen to prove to yourself that it definitely is -1. I find that when students do that, they will recall that information better or be able to derive it on their own rather than making the mistake of just trying to memorize it and then forgetting it for an assessment. Also, highlight the fact that this is a weak base, and so you must use the equilibrium arrows to indicate that. more general definition, and the one that we will typically use in my class, is the Bronsted-Lowry definition. The Bronsted-Lowry definition for an acid is a proton donor. You've already heard me saying that already. It's just, I'm definitely, more comfortable with the Bronsted-Lowry definition. It's more general and more useful in our course here. The base is a proton acceptor. And so the reason why I love this definition is that all you have to look at is a transfer of one proton. Now, something I just want to make note here, that I think one of the hardest things about general chemistry, and I remember when I was a student, it was hard at first to predict products of reactions. It was overwhelming. There's just so much there. And once again, not everything is so tangible to visualize, right? Especially at first, right? You're like, what is going on in this beaker here? At first you might not be quite sure. Now, my biggest piece of advice in my experience of being a student and teaching for many years is knowing the definitions will help you predict the products of the reactions. So knowing the definitions So for example, the main definition you will be using in my course is the Bronsted-Lowry definition. And when you look at a reaction, you ask yourself, what is my acid? What is my base? And say it out loud, right? Talk yourself through it. And if you identify that you have an acid, you say, okay, I know an acid is a proton donor. It will lose a proton. And therefore, my base will take that proton. What do I end up on the product side? Let's do an example together. We all know that hydrochloric acid is an acid, right? Just based on the name. And initially we're going to focus on mixing these with just water as the other reactant. And in a later video, we will eventually start to mix different acids and bases together. We also know that hydrochloric acid is one of the strong acids, so we're going to use this arrow here going straight forward. So the very first thing I do when I have to predict products of a reaction is I identify my acid. And in this case here, water has to act as a base. Remember that one of the mantras in chemistry is that opposites are attracted to each other. Two acids are not going to want to, quote, react with one another. It's always going to be an acid and a base. Later on in organic chemistry, you would learn that it's a Lewis acid and Lewis base, which translates to an electrophile and nucleophile. So mantra is that opposites are always attracted to each other. So I always identify, if I have water as one of my reactants here, I looked at what the other one is. And then I determine what this species is an acid or base, and that will tell me how water will behave. Right? All right, so because hydrochloric acid is a Bronsted-Lowry acid or a Bronsted acid, then I know that means it's a proton donor. It will lose that proton. So I can already write one of my products here, it's chlorine, but it lost a proton, and a proton has a what charge? A positive charge. So this chlorine ends up having a what charge? Negative. If HCl was neutral overall, you've lost a positive, then you end up with a negative. And that's one of the halides, the chloride anion. And then I tell myself, okay, water is a base, which means it's a proton acceptor. So it's going to take that proton and it turns from H2O to what? Right, you just add a hydrogen, just a proton transfer. H3O. We know H3O doesn't exist neutral. What's the formal charge? +1. Fantastic. That's the hydronium ion. Okay? So once again, don't just try to memorize it, derive it. All right, we've identified the acid and the base. Let's check to make sure the charges look good. It's neutral here. Adds up to being neutral here. We're looking good. Another thing I want you to be able to do is identify the conjugate acid and conjugate base, and that's on the product side of your equation. So if we look at hydrochloric acid, on the product side, there's a product that looks similar, chloride, right? They look like they could be related to one another. We would identify chloride as the conjugate base of hydrochloric acid. And I always abbreviate conjugate base as CB. So from here on out, that will be CB. Water has a partner over on the product side that looks very similar, like they could be related. And this one would be the hydronium ions, water's conjugate acid. And this is vocabulary that we will be using extensively from here on out. So it's important that you feel comfortable. If I'm like, what's the conjugate acid of water? Immediately you can visualize, ooh, that's the hydronium ion. And so the partners here, hydrochloric acid and the chloride ion are conjugate acid-base pairs. And water and the hydronium ion are also conjugate acid-base pairs. Conjugate acid-base pairs differ by 1 proton. If we're just looking at the Bronsted-Lowry definition, all we're looking at is the transferring of 1 proton from one species to another. That is it. And the conjugate acid-base pairs, they look like each other, like they're siblings. And the only difference is that one is missing a proton and the other one has it. Same thing here. Water, has H2O, but then it gains a proton, turns into hydronium, which is the conjugate acid. All right. Now, something you will notice is that water can't make up its mind, and we call water amphoteric. And that means it can act as an acid or base. And that's why you heard me earlier say, look at the other species first before you look at water. Water will behave differently depending on what you add to it. Okay? So in this case, water had to act as a base because we have an acid with it. In the previous example, when we were looking at ammonia, at the bottom here, ammonia acted as a base, and therefore water had to act as an acid. What is the conjugate acid of ammonia? Fantastic, the ammonium. Remember, always use the definitions to talk yourself through it. A base, I know initially we're looking at the Arrhenius definition as a hydroxide, producing hydroxide ions in solution, but let's look at ammonia as a Bronsted base, which it is. A Bronsted base is a proton acceptor. So if it accepts a proton, we would expect its conjugate acid to have 1 extra proton, and it does. It went from NH3 to NH4. So here in this conjugate acid base pair, we gained a proton. And water was acting as an acid, and once again, an acid's a proton donor. So it had to lose a proton, it gave it to ammonia, and when it loses a proton, it went from H2O to OH minus, right, the hydroxide. And so therefore, this is water's conjugate base, hydroxide. And you can see that just looking at the transfer of that proton, that we lost a proton here in that process, right? It's just an exchange of one proton. That's all it is for these acid-base reactions that you're doing in second semester general chemistry. Okay, so don't try to make it any more complicated than it is. All you're doing is counting one proton at a time, okay? But knowing the definitions, like I said, is tremendous help. It was for me when I was a student, and I've seen it work for so many of my students, that if they talk themselves through it, they're able to derive it rather than memorize it. They do so much better. So I encourage you to do that now, and so that you feel more confident. So let's go ahead and practice this question here. It says, identify each substance as an acid or base and write a chemical equation showing how it is an acid or a base according to the Arrhenius definition. I'm also going to talk about it through the Bronsted definition as well, because they're both. So for example, HBr is hydrobromic acid. That's one of the strong acids, as the name suggests. So we're going to see hydrobromic acid behave like an acid. The second one is strontium hydroxide. It's a group 2, 2A hydroxide, which considers it a strong base. In later chapters, I'll review over again the strong acids and the strong bases. But it would be helpful for you to do that even now, especially since many of you probably learned that already in your first semester general chemistry course. All right, let's start with hydrobromic acid. Remember, you're adding water. And so the first thing I do is say, okay, I know it's an acid. Just knowing the name itself is a huge clue, right? That can be really helpful, knowing the names of these. Therefore, if hydrobromic acid's acting as an acid, water must be behaving as a what? As a base. Fantastic. And I'm going to go ahead and just use the Bronsted definition, since that's what we will be using from here on out. And then I will refer back to the Arrhenius definition at the end here, just so you understand both of them. So a Bronsted acid is a proton donor, and even writing that down on your paper can kind of just calm some of those fears. You're just like, okay, I know it's just a transfer of one proton. This is going to be okay. We will also discuss, like I said, the strong acids and strong bases. You'll learn them, and then everything else will be considered weak. So in this case here, we know it's a strong acid, so use only a single arrow, not a double equilibria arrow. And if hydrobromic acid's a proton donor, then I'm going to lose that proton, and I'm only left with bromine. But what formal charge does the bromine have? I lost a positive charge. I end up with a negative. Fantastic. If you ever wanted to derive that for the halides, if you're like, how am I supposed to remember that? I need to derive it. Then you can always draw out the structure here. Bromide looks like this. So it has those 8 electrons. Typically, it's in group 7A, so it would have 7 valence electrons minus the 8 that we've just drawn in. That's the reason why these halide anions are -1 formal charge. So there's bromide. Water is acting as a base, so it's a proton acceptor. It turns from H2O to H3O, which is not neutral. It has a what formal charge? Correct. It's the hydronium ion. Has a formal charge of +1. Also, the bromide ion would be identified as the conjugate base of hydrobromic acid. They're partners. And the hydronium ion would be considered the conjugate acid of water, because they're conjugate acid-base pairs. They're partners as well. Now, the way we derive this using the Bronsted definition still follows the criteria for the Arrhenius acid definition. Remember the definition of Arrhenius acid is it produces hydrogen ions in solution, and we do see that hydrogen ions were produced. All right, let's check out strontium hydroxide. We've identified strontium hydroxide as a strong base. Remember, we're mixing this with water. Now this is a little bit different. We're doing the Arrhenius definition here. The Bronsted base definition will work better for when we start doing the weak bases of our ammonia derivatives. But for this one, the Arrhenius definition is it produces hydroxide ions in solution. Since it's a strong base, we use a single-headed arrow going forward, and it dissociates completely into the strontium 2+ cation plus 2 hydroxides and then just to have it balanced, this looks a lot like the sodium hydroxide equation we did earlier in this video. So we can simplify. The strontium hydroxide definitely follows the Arrhenius base definition, where it is producing hydroxide ions in solution. All right, so make sure you review over your definitions. You begin practicing predicting the products of some of these acid-base reactions, whether they're strong acids, they're strong bases mixed with water. And get a little bit more comfortable definitely with the Bronsted-Lowry definition, proton donor, proton acceptor, since that's the definition we will be using the majority of the time in the next series of videos. Thank you all for watching, and I will see you next time.